Hey everyone, welcome again to our CA tutorial. In this particular tutorial, me, Shahroh Yahyaev, is going to analyze LC-3 machine language problems and basically assembly language. So before the beginning of this tutorial, I want to just tell you that you have to watch all the series of these CA tutorials if you want to get a good score in your CA and not to fail. And again, before beginning of this tutorial, I want to just inform you sorry for the noise around because there are so many people in my home. But anyway, let's start. So, firstly, you have to understand that there are 7 registers in LC-3 machine, and each register holds 16-bit data. So, one word 16-bit data is transferred between registers. Okay. So, and that means each instruction has also 16 bits. That means, for example, if you think that this is instruction, okay, and this instruction is 16-bit, okay. So as you know, there are several operations that you can do in LC-3, and the operations are called in assembly mnemonics. For example, there are such operations like add, okay, add. That means after add you just pass either 2 registers, destination register and source register, and yeah, again source 1 and source 2. This is example, okay. So what does this operation mean? This is LC-3 assembly mnemonic, okay, assembly mnemonic, so assembly operation. So that means that you are going to say that just add the value inside the register R2 and R3, and the result please store in R1. Okay, so the very fundamental thing to understand that this register, this instruction is 16-bit. Okay, let's take this as an example, and each instruction, it doesn't matter whether this is add or, for example, and, okay, or not, okay, doesn't matter. Each instruction, each operation in its 16-bit machine language form. This is kind of, okay, this is machine language form, okay, machine code, let's say. Each instruction in its machine code, its first 4 bits, okay, its first 4 bits identify the operation. This is called opcode. What does mean opcode? Opcode specifies which operation is executed in this instruction. Is executed in this instruction, okay. So what does it mean? This opcode is kind of an idea of operation. For example, opcode of this add operation or instruction is 0001. So whenever you see this long instruction, 16-bit instruction, and whenever you see that the following first 4 bits are 001, you have to understand that this is instruction of add the operation, okay. And the result of 12 bits differ according to of course operation. So before considering the problems, let's see what kind of operations we have. And there are 3 types of load operations. So firstly, let's consider these ones. There are 3 types of load operations, actually 4, but let's consider firstly 3. And as you can see, here we have what? First 4, this is of opcode. This 0010 specified that this is just load operation. And what does mean DR? DR means, okay, we're going to meet this DR in many places, so that's why I'm going to write here that DR is just destination register. This is destination register. So and then we have PC offset 9. Here, what does it mean, PC offset 9? It means that just the value, I mean 9-bit value, 9-bit number. Offset is a number. What does it mean? Actually, what does it mean? What does this operator or operation does is just puts the data in some memory. I mean, load operators. I mean, just remember that the load operations do what? They just go to the memory. I mean, load operations just go to the memory. For example, this memory, they take some value and put it into some register, okay, some R. So what does this load operation does is, as you can see, this one it calculates address. How does it calculate? It just adds incremented PC and this 9-bit value. For example, consider that PC has instruction. I mean, PC is a program counter that has the next instruction. For example, let's come here. Let's say that we are now, not we are now, but let's say PC has now value, for example, x 0x3000. And what does it mean? We are now in this instruction, and while we are now here, and while in kind of executing this instruction, during the execution of this instruction, PC is incremented, okay? So PC is incremented, so now this is 3001, okay? So this load operation, what does it kind of firstly evaluates the memory address. So how does it evaluate? It adds this to this PC incremented. This is PC incremented plus the 9-bit value binary number that you give. Okay, and then for example, let's say this 9-bit binary value is, for example, 0000, 4 zeros. Actually, this is signed integer, so this 0 means, leading 0 means this is positive number, and 0000, let's say 1. So this is 1, right? So what I'm saying is that you just add 1 to this PC incremented value. So following that, we have what? This address, 0x300, and then here 2. And what does it mean? We have dr, right? I mean, here we have dr. So I'm just explaining. I'm not going to explain each operation, just I'm explaining how to understand the operations, okay? So then what does it? It goes to this memory address. For example, let's say here we have memory block, this 3000, and here also 3001, and here 3002, and it takes this value and puts it in destination register, okay? So just remember, load operators, any type of load operator, firstly, let's say, evaluate address. Most of the time, just adding this offset, this is called offset, to incremented PC, okay? This is incremented PC. This is just value, offset is just value, and then go to memory, copy the value layer to dr, okay? Easy. So and there are load indirect operations. I mean, this is just does what? Okay, as you can see, you can analyze everything from here, but the logic is that you kind of evaluate this memory address, and you take this memory address as not address, but again address. So you can again evaluate the address, and then from this address you kind of get the value and put in dr, okay? Everything is very easy. So in load base offset, as you can see, you have destination register, but in this case you have base R. What does it mean? Base address. So you add to base address is 6-bit value. For example, you have a list, and for this list, the name of the array of a list is always points to the base address, okay? So let's say base address is 2000, and offset, we're going to, for example, access this 6 element, yeah, so in this case offset is going to be 6. So as a result, gr is going to be m0x, I mean this one is going to be 2006. So we're going to the memory block with address 2006, for example this is 2006, and getting this value and putting it inside destination register. So I think this is pretty easy for you, I hope. So let me delete unnecessary stuff. So again, let's continue. So then we have this store operations. I think now you understand how to just understand the operations. It's just pretty easy. What the store operation does is just takes a value from the register and puts it to the memory. So load does what? Takes from memory, puts to the register. Store does what? Just takes from the register and puts to the memory, just vice versa. Okay, so then we have our very important one, add addition. So you know, I've shown you one example of addition where, okay, so where, as you can see, we have this instruction, right? I mean 3 registers, destination, source 1, source 2. So yeah, here this one. So first 4 bit, of course, opcode. I mean this is opcode, right? Then destination register. Just please remember that registers are 7. There are 7 registers. So as you can see, 7 can be represented with 3 bits, right? So this is 111 is going to be 7. So those registers are represented with 3 bits. So each register takes 3 bits in instruction. So that's why from 11 to 9 it's going to be destination register. So 11, 10, 9. So destination register, source 1, source 2, and between source 1 and source 2 you put 3 zeros. Okay, sorry for the noise around, but as you can see, this just given here, everything is given for you. You just don't have to memorize anything. But if you want to kind of, for example, add for example the constant, let's say, so why I'm drawing here, so let's say we're going to add constant, for example add r1, this is destination, okay, this dst, then r2, I mean just add, this is source 1, and then if you want to specify the constant, you just put this sign and just write the decimal value. So this is going to be a constant, and what does it mean? This r1 equals to r2 plus 2. And in machine code you do this, okay, you do this like this. You specify dr as we done in previously, source 1, but then instead of 0 here you put 1. At 5 index you put 0 if your second source is register. For example, if it's register, then you put 0. If not, you put 1, and then the remaining 5 bits are given to this what they say, constant value. So yeah, in with 5 bits you kind of write the, in 5 bits you represent your decimal number. For example, in 5 bits your 2 is going to be what? 0 0 0 0, no, sorry, 0 1 0. So this is going to be 2 in 5 bits, so you're going to put 2 here. So yes, we have discussed enough. You can understand other stuff yourself. Just, I mean, what I mean is that you can analyze, you know how to analyze operations, right? So now I'm going to solve these problems. So problem number 1a, what they say is that you have this r1, and you have to kind of put 91 to r1. Okay, so finally we have to have r1 with the value of 91. So let me choose different color. So assume that your memory and register are empty and try to make it run as fast as possible. So write your semantics or instructions to the right of your instructions. So firstly, just try to understand that now we're going to do to use add operations, because we want to kind of end up with a value of 91 in R1. Initially, as you see, R1 has 0. But just please remember, in add operation, we have only 5 bits. 5 bits given to our constant value. So that means we can store maximum how big number. So just let's analyze. So why I'm doing const like this. So let's analyze. So if you have 5 bits, you can store a maximum 15. Yeah, 1 1 1 1 1 0 1 2 3 4 15. Just stop. No, not 15, because yeah, 15, but the fourth, this one should be 0, because this is a signed integer. So the very first bit is signed. Okay, first bit is signed. So if it's positive, you put 0. If it's positive, if it's negative, you put 1. So maximum numbers that you can represent is 15. So this 8, 4, 12, and then 2, 14, and 1, 15. Okay, so those, it's not impossible just to with one instruction put 91. Okay, so that's why firstly let's just add 15 to R1. R1 is 0. So now I'm going to do what? I'm going to store result in R1, and what I'm going to store is I'm going to store the addition of R1, which is 0 plus 15. So the very first 4 bits, as you know, is what? Opcode. So I'm going to put this opcode 0 0 0. You don't have to memorize, just put it. So now you have to put destination register. What's our destination register? This is R1, and as you know, as I've told you, registers are represented in 3 bits. So we have 7 bits, because so R1, 1 is going to be represented in 3 bits, 0 0 1, as you can see here. Not auch, I'm just learning German, so that's why I'm saying also auch. In German, just know that also means auch. Okay, here also 0 0 1. This is easy. And after that, I'm going to put source. I'm going to kind of give the source register 1. So source register 1 is also R1, as you can see. So R1 is just 0 0 1, and just please be careful here. So after that, at 5th position here from the beginning, 0 1 2 3 4, you put 0. As I told you, you put 0 if your second source is a register, the value inside a register, or you put 1 if your second source is constant. So I'm going to put here 1. Okay, because as I told you, 15 is constant. So I'm going to represent 15 in 5 bits, but just remember, just do not forget that the very first, the most significant bit, this is called the most significant, but this is not the first bit, most significant bit. Okay, not first bit, most this is represented as MSB, most significant bit, the last bit from the beginning. Okay, I hope you know it. So then I'm going to represent 15. So this is going to be 0. This is positive. So 1 1 1 1. Pretty easy. Okay, so now you have in R1 15, and just let's analyze what should we do next, because you have to represent it. We have to run it as fast as possible. So we have just R1 with a value of 15. So now I'm going to not add again like R1 equals to R1. I'm going to do like that. Actually, I'm going to add R1 to itself and store it in itself. That means I'm kind of multiplying it by 2, right? I'm just adding 15 plus 15, and I'm ending up with 30 again in R1. So this is kind of same with R1 multiplied to the 2, but we don't have multiplication. Anyway, we're doing like this. Okay, so then our R1 becomes 30, and after that I'm just adding the second register. I'm using temporary register. Let's say I'm using R2, and Then I am adding again R1 to R1. So R1 is 30, and now R2 is 60. Okay, so then I'm adding R1 plus R2 and storing it in R1. So R1 was 30, R2 was 60. So I'm ending up with 90. As you can see, if you do here, if you store here 30 plus 30, 60, not in R2 but R1, then you will have R1 60, and when you add R1 to R1, you will end up with 120. But you know, we wanna just store 91 in a register 1, so that's why in order to not to extend, not to get larger than 91, I'm just using this temporary register, okay? Temporary register, which is what? R2. So then I'm adding R2 60 plus R1, which is 30 from here, right? And then I am storing this result in R1. So R1 has now 90. So finally, in order to just store 91 in R1, I'm just adding R1 equals to R1, which is 90 plus 1. Okay, so I'm ending up with 91. So now I'm going to do this one, then this one, then this one, then this one. So let's now do this one, R1 plus R1. So now our R1 is 15. So what I'm doing is R1 and R1 plus R1, so that then this is comment here R1 is 15. Now R1 is going to be 30. So what I'm doing is, so I'm doing what again? Add operation. So for first 4 bits, most significant 4 bits, not first 4 bits, but most significant 4 bits are going to be opcode 0001. And then I'm going to specify destination register. Destination register is R1, which is 001. And then I'm going to specify source number 1. Source number 1 is again R1. So I'm here, okay? Or here, doesn't matter, okay? Source 1. So 001. And then, very important stuff. So then you have to choose whether your second register, sorry for the noise again, whether your second register is source register or constant. If constant, you write 1, it's 5th position, or if it's not constant, you write just 0. In our case, R1 is source register, so that's why I am following this semantic, not this one. Initially I followed this one, but now I am following this one, okay? So this I'm putting 0 at 5th position here. I put in 0, and then I'm putting 2 zeros. This is given for us. I'm putting 2 zeros because I need only just 3. I need only just 3 bits to represent the register. I don't need just 5 bits as this constant needs, okay? So that's why we just put 0, 0 to these places, to these cells, and I'm going to represent this source register 2 in 3 bits. So our source register is also R1, which is 001. So we're done. So now we are here, okay? So now we are here. I'm going to add again R1 to R1, but the result I'm going to store in R2. I am going to do the same stuff, R2, but now R2, I'm going to store in R2. Source register 1 is R1, source register is also R1, so I'm going to end up this R1, R2 with the value of 16. So the instruction is pretty same as this one. However, we will come to the difference here. Opcode is the same, but destination register, here it was R1, but here is R2, so R2 is 010. In binary 2 is 010, but the rest of the stuff is the same because source register is also R1. I am kind of assigning the second source to our second source is also register, so that's why I'm putting here 0. If it was again it was constant, I had to put 1, and the remaining 5 bits I had to use to store the constant, but here we have register. For register we need only 3 bits, so that's why I'm putting here 0 0, and the remaining 3 bits I'm going to use for second source register, which is also R1, which is also 0 0 1. Whew. And now here we are done with this one, and then we're going to kind of do this operation R1, I mean here R1 plus R2, 30 plus 60. So 0 0 0 1, just firstly let's write it here, R1, I'm going to add R1 plus R2. Okay, then R1 is going to be 90, because I'm going to add these two numbers. So our source register is R1, right? I mean 0 0 1, and our source, no, I'm destination register, this is destination register, sorry for confusion. Our source number 1 is 0 0 1, this one, and then I'm going to put 0 here. Sorry for the noise around, because so many not good people around me. Okay, they're making noise. You don't understand that I'm recording the video for many people, but anyway, let's continue. I'm putting here 0 because our source register, I mean our second source value is inside the register. Okay, so 0, and I'm putting here 0 0 because I don't need 5 bits, I need only 3 bits. So our source register number 2 is R2, which is 0 1 0. Okay, R2 is represented in 0 1 0 in binary. Okay, so finally we have in R1 19, so I'm going to add just 1 in order to end up with 91. Okay, 0 0 0 1, I mean let's write it here R1, and I'm going to add R1 plus 1. So then our destination register is 0 0 1, and our source register 1 is R1 0 0 1, and then I'm second, not I am, but my second source is constant, thus I am putting here 1, and the remaining 5 bits I'm going to use for identifying, for writing the constant, which is 1, which is 0, I mean this is sign, and then the remaining 4 bits for the actual value 0 0 0 1, because this is the binary representation of 1 in 4 on 5 bits in signed form. Okay, so finally we have R1 is equal to 91. So this is the end for the part A. Okay, so let's quickly analyze part B. In part B you have now, I mean it says you have in R1 now 91, and your task is now to perform this operation, I mean to write the logic for this operation, so that finally we will have 91 multiplied to the k, multiplied to some constant, and we will kind of have to store the final result in R0. Okay, everything is now have to say clear, but before filling this table, we have to understand the algorithm, so now let's first understand the algorithm. So we are putting putting 0 to R3. So whenever before doing anything, you have to initialize a register. So let's where to write, let's write here. We are putting R3 to R3 0, and then as you can see we are loading, this, you're given this instruction, not instruction but semantic. You have to understand what operation should I choose. As you know, this is M, and here inside this square brackets this is the memory address. So you have to go to this memory address. This is 3100, and take the value inside this memory address and put it inside register R2. This is not bad load operator. As you can see, semantic is the same. Don't pay attention to this big long expression. This expression is just in this case 3100. Okay, yeah, 31, this one 00. We are going to this memory address, this one, and putting it in destination register, which is in this case R2. So you will be given such semantics, and out of this semantics you have to understand which instruction to choose from this given table. Okay, so now I'm going to write 16-bit instruction for the load. So what is I mean the most significant 4 bits are opcode, and what's opcode of load is this one 0010. So 0010. So let me do it like that. So then seconds then I mean following 3 bits, okay, the following 3 bits is destination register. So in this case our destination register is R2. So R2 is what? Nothing but 0 1 0. Okay, so the remaining 9 bits are represented by value, I mean offset. Offset is what? Actually what does this expression equal to? Let me explain it here. This expression equal to what? I mean, as we know in the load means what? GR, destination register, PC incremented plus offset. Okay, in this case our PC plus offset equal to what? 3100. And now we have to understand, we need the value of offset, but you know, in order to find the value of offset so that we can put it in our 16-bit instruction, you have to subtract this 3100 minus PC incremented. So how we can find PC incremented? So you know, here I mean now currently our PC is this one. So our PC is incremented PC, okay? I mean, during the execution of this instruction, our PC is incremented, so now PC incremented equals to this one, okay? I repeat, while you execute any instruction, your PC is going to be incremented. So currently our instruction, this one, this current PC, this is current PC, but during the execution it will be incremented, so this is PC incremented. So that's why here I'm going to put what? Here I'm going to put 3002. Sorry for the noise, okay? There's some man. So okay, so then we have to kind of calculate this value. So this is in hex, right? I mean 3100 in hex. So in hex is going to be what? Let's calculate 0, I mean 3 0 0 1 1. I mean this is 3, and 1 is going to be 0 0 0 1, and remaining 2 zeros are just 8 zeros. And now I'm going to subtract this one. So 0 0 1 1, this is 3, I mean this is this 3, and then 8 zeros because we have this 2 zeros, and then we have 2, right? 2 is going to be 0 0 1 0. So this is how you kind of calculate the offset, okay? So you just use this one, and it comes here. Here we have what? 0, and then have here what? Not 1 but 10. 10 minus 1 is 9, but you write just 1. And here in this cases we have 9, right? Because for example we give to it 1, it becomes 10, but when you give it to here it becomes, I mean this becomes 9 and this becomes 10. When it gives to this one, I mean following it becomes 9. So anyway, all these zeros now, I mean including this one from here, are 9s. So 9 minus 0 is 1, okay? So let's yeah, so yeah, 3 4 5 6, yeah, how many we have? 1 2 3 4 5 6 7 8. So 8 1 2 3 4 5 6 7. So again 1 2 3 7, yeah, I mean put here, I mean 1. So I mean this was 1, and it gave to 1, it's 1 to this 0, it becomes 10, but this becomes 0. So this overall, this is 0, okay? So sorry for the noise. So I mean this is a 9-bit representation of the offset. I mean the remaining everything is 0 because we don't need this truncate. So this is your offset, okay? I hope now you understand how to calculate the offset. So you calculate it, I mean you just subtract the value from the value inside this M, memory PC incremented. PC incremented is the next instruction, okay? For example, if you are here, your PC incremented is going to be this one, okay? So let's put everything here. I mean, this 9-bit representation of the offset is supposed to 0, 1, 1, 1, 7 ones, and then finally 0. So yeah, done. So after that, we have this condition. But before moving condition, firstly, I'm going to just tell you that what we have done here. It says that at the memory location 3100, the value of k is stored. So we did what? We just went to this memory location and got the k and put it inside R2. So now R2 has k, okay? So remember, we're going to find this the value. So again, second instruction was what? R2. Let's say just we put k, okay, instead of just writing this one M3100. Just for simplicity, let's say we loaded k. Loaded means took from the memory and put into the register to R2. And now we know that in R1 we have 91. So our logic is going to be what? So consider that we have n, this is 91, let's say, and k, this is 3, and we need output 91 multiplied to 3, okay, some value, okay, 3, this one. So what I'm going to do is I'm going to kind of do a loop. I mean, use loop, for example, while I'm going to do like that, while k doesn't equal to 0, I'm going to just let's say I'm initializing one result variable which is set to 0. I'm going to store the result in R variable, so I'm going to just add I'm going to do what? Just add R plus n, okay? And then I'm going to decrement k and do it until, and then return R, and do it until k is not equal to 0. For example, this is our k and this is our R. So k is equal, initially k is equal to 3, so it's not equal to 0. So that's why I adding 0 plus 91. And now our R, this is R equals to R plus n, and this is our new value. It's going to be 91. And then I'm going to decrement k, and k becomes 2. 2 is not equal to 0, so that's why I'm adding to R, which is 91, plus 91, which is n. So our result is what? 182. So then k is again decremented and becomes 1, but 1 doesn't equal to 0. So those I add to R, which is 182 plus n, okay, 91. So result is 273, and then k is going to be decremented and k equal to 0, which is equal to 0, so we're going to terminate. So I hope that algorithm is pretty easy and explainable or understandable for you, okay? So let's write it here. So what does it say? If R2 equals to 0, which is k, right? This is what? If k equals to 0, if k equals to 0, that means branch out of the loop. That means, this is branch to start of the loop. What does it mean? Branch out of the loop, that means that, for example, this is the loop area, so you have to just jump here. Here's the last instruction. What does it mean, branch to start of the loop? That means just go to the beginning of the loop, which is this one, condition. Because as you know, the very first thing that you do in the while loop, you just check, okay? This is condition number 1, right? This is condition number 1. So this is condition number 1, and this is condition number, no, not the condition, but operation number 2, and this is operation number 3. So condition number 1 or operation number 1 is condition, checking the condition whether k is equal to 0 or not. So if it's equal to 0, as you can see, if it's equal to 0, we're going to here to the done state. This is done, right? This is the final instruction, which is in our algorithm. Sorry, in our algorithm, this is, oh, what I've done. In our algorithm, this is this one, return, okay, if true, that if k is equals to 0, okay. So now to write this kind of branches, we have this instruction called branch, as you can see, branch. So the opcode is 4 zeros, and then here's this NZZP. NZP means what? N means this NZP are, as you know from system programming, flags. So N means negative, Z means zero, negative flag, zero flag, and P means positive flag. This let's say flags, let me write here, this flags, oh come on man, these flags are not but 1-bit flags. I mean N, Z, P. If N is 1, Z, that is 0, P 0, what does mean? That the value is negative. Okay, if N0, Z1, P0, that means the value is what? 0, equals to 0. If 0, 0, 1, that means the value is positive. If 0, 1, 1, that means it is either positive or equal to 0. And let me delete this one. Oh, what I'm doing. So if the value of NDP, 3-bit numbers are 1, 1, 0, that means it is either negative or equal to 0. And this seems like, just like that, okay? For example, in order to write this condition, whether R2 equals to 0, in order to check it, so this is N, this is Z, this is P, I'm going to just write here 0, 1, 0. What does it mean? That this means that the value R2, the register, the value of the register, which is checked now, should be equal to 0, so that we can kind of jump to here. Let's come here. You put here PC offset. PC offset, because if this condition is met, for example, now I've written here, in table 0, 1, 0, that means if 0 flag is on, okay? That means if 0 flag is on, then we have to jump to somewhere. So this memory address is going to be calculated with PC incremented. If PC, you know what does PC incremented mean now, right? PC incremented plus this 9-bit offset. I guess now it's understandable for you. So now I'm just writing here 0, 0, 0, which is opcode of the which is opcode of the branch. So then I'm writing 0, 1, 0. I am saying that if the 0 flag is on, then jump to somewhere, and this somewhere is calculated, as I told you, PC incremented plus offset and 9-bit offset. So our PC incremented is what? This is our current PC. Let me delete this one. This is our current PC, okay? And our PC incremented is going to be this one. This is our PC incremented. And we have to jump outside of the loop. This is the end block of the loop, and this is the outside of the loop, right? So I have to jump where? As I told you, this is the area of the loop. This from 3 to 5. No, from 2 to 5. So the outside of the loop is this point, this instruction. So I'm going to jump to instruction 3006. So this one, our PC incremented is what? PC incremented plus offset, right? As I've told you, our PC incremented is this one. So 3003. So our offset is going to be what? This is 6, this is 3, so it's going to be just 3. Okay, actually, yeah, 3, or you can say, it doesn't matter, you can say in hex this one, 0003, doesn't matter. In 9-bit representation, the very first bit is sign bit, right? 0, and then 7 zeros, 4, 6, 5, 6, 7, and then 1. Okay, yeah. No, stop. Two ones, because you know this is one, but we need 4, 5, 6, 7, 8. Yeah, 9 bits. 9-bit representation of 3. So I'm writing this one here. 3, 3, 3, 3. I mean 0, 0, 0, 0, 0 and 1. Let me delete these ones. Yeah. Here we have what? 1, right? This is offset. This is a 3. I mean, this is offset. This is 3. We're adding this 3 to our PC incremented. Then, if the condition is met, if this condition is met, we are going to jump to here. Okay. So let me delete unnecessary stuff. I hope you are just getting everything. Hopefully you are getting everything. So let me delete. Let me quickly write everything. 0, 0, 0, 0. I mean, the last is 1, 1, 0. Okay. So I don't like this mess. Okay. So yeah. Perfect. So now we're writing this very first operation. I mean we're writing the machine code for this check operation. Now I have to write machine code for the second operation inside the loop, which is r plus n. As you know, r is a variable where we're going to store our final result. But here we're given that you have to. Here we're given this r3. R3 is already initialized, so that's why I'm going to assume that r3 is r. Okay. R in our formula. Okay, so that's why here R3 we're going to store result in R3, right? Here we're going to store result R3, and we're going to add R3 plus n. N is 91, and 91 is stored in R1. So I'm just writing that R3 store result in R3, addition of R3 plus R1. So you know now how to do it. Just pause the video and do it yourself. I mean, the opcode for the add is 0001, and then you specify destination. Destination is R3, right? R3 is 011 in binary. 011 is 3. Then you specify source 1. This is also 011, and then you write either 0 or 1 based on your type of your second source. In this case, I repeated it 100 times. Our second source is register, so that's why I'm just writing here 0, and then I'm writing 2 zeros because I need only 3 bits to represent the register, and our second source is R1, which is 001. Okay, so done. So now I'm coming to third operation, which is going to be what? This one. K minus 1. I'm just going to decrement k. Okay, so for this what we have, so just we do again what? I mean, add operation. So 0001, this is opcode. I'm doing what? R2. I'm storing result in R2 because R2 has a value of k. What I'm doing is R2 plus minus 1. Okay, because you know this 9 offset, I mean 9 bit integers, this is a signed bit, so we can represent minus 1 also. We don't have subtraction operation, we have addition, so that in order to perform r minus 1, I'm just doing like r2 plus minus r1. So this equals to r2 minus 1. Okay, so our source destination register is r2, which is going to be 0, 1, 0, and then our source register 1 is r2, 0, 1, 0, and then you know I'm going to put here 1 because my second source is constant, and I'm going to represent this constant in 5 bits. And yeah, r1, as you know, r1 then is going to be what in the signed integer is going to be just 1, 1, 1, 1, 1. Okay, so this means that this is a negative number. I mean, signed bit means 2's complement, right? I mean, in 2's complement, minus 1 is 1, 1, 1, 1. This is in 5-bit representation. Okay, 5-bit representation, where the first the most significant bit is signed bit. Okay, so for example, if you write 0, 1, 1, 1, 1, it's going to be 15, right? Because this is positive number. That means positive number because it's 0. So then overall it's going to be 15, but if you put here 1, this is going to be a negative number, negative representation of the 2's complement binary number. So I hope you know it, okay? No need to explain it more. Just this 5 ones, it means -1. So for example, in 8-bit representation, -1 is 8 ones, okay? I hope it's understandable for you now. So we're done with this loop. I mean, we written, not written, but we kind of expressed these 3 loop operations in machine code in LC-3 machine code. So, right? But you know, at the end of the loop, we're going again to come here, right? To check position. So let's write this branch. This branch is going to be what? Branch to start of the loop. It's going to be what? Just jump, right? I mean, there's nothing to check. We're not checking anything. We need to just jump. So in these cases, this is called unconditional jump. Just please remember, unconditional jump. That means you jump always, doesn't matter, okay? You don't check anything, you just jump. In this case, you just put just 1 1 1, okay? You just set n z p all the flags to 1 because you don't check anything, because it's always 1. I mean, doesn't matter, you have to jump, okay? So yeah, opcode for what was it, branch is going to be 0 0 0 0, and then I'm just going to put the offset, 9-bit offset. So you know, offset is I mean, not offset, but the location to jump. I mean, the location where to jump is calculated by PC incremented plus offset. And you know what, we are going to jump to the beginning of the loop, which is here. So the final value should be 3002, because we're going to jump from 3005 to 3002, and I'm recording the video. And those we're going to calculate it by PC incremented, which is what? Our current PC is this one. PC incremented is going to be this one. So yeah, this 3006, right, plus offset, and this everything is equal to 3002. So yeah, now I'm going to see, we are seeing that offset is going to be what? -4, right? -4. So then you have to represent this -4 in 9-bit signed form, which is going to be yeah, let me delete this one. I'm just writing the value. Okay, this is a signed bit, so I'm going to put 1 because it's negative. Send 1 1 1 1, and this is in 2's complement, so you can check whether this is true or not, but I already calculated it. So yeah, we have written this one. So finally we're going to put, I mean, copy the value of R3 to R1, because we're instructed to store result in R0. So, but you know, there's no operation to copy the value. So if you, for example, if you have R0 and you have R3, for example, it has, for example, some value K, you can just literally copy the value here in R0. You do what? You just add R3 plus 0 so that it will be copied, right? So that's why I'm just putting here plus 0, because there's no copy operation. So I'm just adding 0, which is not changing result, and copying the result to R0. So our add operation is going to be what? 0 0 0 1. This is the opcode. Our destination register is going to be R0, which is 0 0 0. In 3 bits, 0 is represented with 0 0 0. So our source register 1 is going to be what? R3, which is 0 1 1. And then I'm putting 1 because the remaining 5 bits is going to be represented, or is going to be given for representation of 0. So 0 is represented in which fashion? In 5 bits is represented 0, which is a sign, and 4 zeros, okay? Just zeros. So this is all. Hopefully you understand it now better. Because of time issues, I'm just not going to do this one. I'm just going to give you kind of assembly mnemonics operations, so that you will yourself transform it to, how do you say, machine code. So this one is going to be what, you have to kind of do this operation r1 minus r2, and you have to store 2's complement of r2 in r5. That means there's no r1 minus r2, there's no subtraction, right? So that's why you do what, you do r1 minus plus minus r2. So you have to kind of multiply r2 by minus 1, or there's no multiplication, but you have to kind of change the sign of r2. For this, you have in 2's complement, you have to kind of do what, you have to negate it. So you can find the opcode everything above in the table. So you do what, firstly you, let's write here, firstly you not negate it. I mean, this not operation, not r5, result store r5, source is r2. So just store the note of negation of the value inside r2 in r5, and then just add 1 to r5. I mean r5, this destination, source 1, then second source, and then perform this operation. I mean add, store in r4, add what, r1 and r5, which is minus r2, right? r5 is minus r2, and then you write this condition, this branch. I mean you put this, I mean you check whether r4 is positive or equal to 0. So NZP, you use branch operation, your NZP is going to be set to what, 0 1 1, because it should be on when it's equal to 0 and bigger than 0 if it's positive, right? So you have to put here 0 1 1, and then you have to swap the value of r1 and r2, and as storing the temporary value, you have to use r5. So you can do it like this one. For example, you have r1 5 and r2 4, you're going to end up with r1 4 and r2 5. In this case, what should you do? You have r5 temp, I mean this is temp register. You have to do what? You have to add and store result in r5. You have to add r1 to 1 0. That means now r5 is 5, and then you have to store result in r1 and add r2 to 0. That means this is what, r1 equals to r2 plus 0, which is going to be what, 4, because this is 4 plus 0 is going to be 4. And then finally you have to do what, you have to store the result in r2 and add to r5 0. This is going to be what, r2 equals to r5 plus 0. r5 was 5, which is r1, so 5 plus 0 5, I mean 5. So finally you have what, I mean in r1 you have 4, in r2 you have 5, which was our objective. So you do these operations, you put these 3 operations here in this 3, and then finally you have to copy the value of r2 in r2. You do what, as I've told you here, there's no copy operation, you just add to r2 0. So your mnemonic is going to be what, add r2, this is destination, source register 1 is r2, and your constant is 0. So I hope everything was pretty understandable for you. This part I'm going to leave it for you, because after analyzing this everything, you should be able to solve this yourself. The main thing is to find out the algorithm. You know, you're a programmer, right? You have to find out algorithm yourself. My task was just to explain you have to kind of represent this algorithm, let's say this algorithm, in machine code. So thank you for your attention and good luck in your exams.